So hello everyone, this is lecture 7 for the quantum mechanics. So today we will study the Einstein interpretation of photoelectric effect. But before that, let me give you the solution for the questions we were discussing. So I gave you this question. So I will solve this first part only, others you will do the same. So it is given that power is 1 watt, so means energy is radiated 1 joule per second, okay? And this radius is 1 meter. So you will find this is whole sphere is formed by this source. So energy per unit area means energy on the sphere per unit area. So area of the sphere is 4 pi r square and energy is 1 joule per second. So 1 upon 4 pi r square will give you energy per unit area. Now only this 1 angstrom radius area can give the energy to electron. So we'll find the energy at this point, means in the area of with this radius. So area by this 1 angstrom radius will be pi r square. So pi radius is 10 minus 10 meter square. So this will be your area, and this is your r is 1 meter. So this will be energy per unit area. So at this area you will get 1 upon 4. This means this amount of energy is falling at this point. Now total energy required to remove the electron is 2.1 electron volt. So 2.1 electron volt in the joules will be 2.1 into 1.6 multiplied by 10 to the minus 19 joule. Now per second how much energy is falling? This. So divide by this will give you total time to make this 2.1. Okay, to make this value. So divide this energy by this energy, you will get your answer as 138 seconds. So in minutes is nothing but 2.3 minutes. So that's how you can find. Means classically it will take this amount of time to emit the electron, and as the power decreases it will take more time, and as the power increases it will take less time. So that's how you can see this thing in the classically. Okay, and there was one more question I didn't give you the solution, so I just forgot that. So this was also the question. Now you can find the temperature using the Wien's displacement law directly. T will be 2.8 divided by this lambda max, and to calculate this intensity you use the sigma this and use this formula, and this will give you the intensity. And temperature you will find from here, from the first part, just substitute here and sigma here and C you know, so you will get the intensity. Now let's move to the today's topic, that is photoelectric effect and the Einstein interpretation of photoelectric effect. So we discussed that in Planck theory, that using the Planck theory how we get this result. So in the last lecture we discussed about the results or the observations made in the 1887 by the Hertz in the experiment due to the that was photoelectric effect, and we studied that what were the failures of classical physics in that case, in the case of this effect. Then we will see the now Einstein interpretation of photoelectric effect and how he explained all that failures and the explanations of the failures. Okay, so Einstein interpretation of photoelectric effect. Einstein used Planck's quantization of electromagnetic radiation to explain the experimental observations of photoelectric effect. So he used the Planck's quantization. He better used, means that thing means energy will be quantized or the discrete. So he used that thing to explain the photoelectric effect, and he was able to explain this. So let's see how. So he assumed that the light is made up of corpuscles, that is photon, each carrying an energy equal to h nu. So what is the difference between the Planck's theory and this Einstein interpretation? So in the Planck's theory we assumed that energy can be of h nu, 2h nu, 4h nu. So it can either take 4h nu, 2h nu or h nu. So these were the packets in the form of this. It can be this energy, it can be this energy, it can be this energy. But Einstein assumed that each packet will have h nu energy only, and we call that packet as photon. So it won't be 2h nu, 3h nu, each will be h nu. So if there is this radiation, so if it has some E equal to NHU number, so it will have n photons. So in the Einstein theory we have significance for this n, but here there is no significance. Here it means it can be 3h nu of one packet, it can be 2h nu for one packet in the Planck's theory. But Einstein said that if it is nh nu, then it will contain n photons. Okay, if this radiation has energy nh nu, then it will contain n photons, and each photon have energy h nu. So this was the difference in the Planck's theory and the Einstein interpretation of Planck's theory. So this was the first assumption. Second was, he also assumed that in the photoelectric effect, one photon is completely absorbed by one electron in the cathode. So Einstein assumed that only one electron will be absorbed by the, means only one photon will be absorbed by the one electron to emit. Okay, so this was the second assumption. Now how these assumptions explain the photoelectric effect or the observations we had in the here. So how this assumptions explain those observations? So let's see. We know now if frequency is greater than a particular frequency or threshold frequency, then electron will eject, because the photon will be absorbed by the electron and it will emit if frequency is greater than mu naught. An electron will absorb one photon of energy h nu irrespective of intensity. So whatever intensity there is, so it won't depend on the intensity, it will depend only on the frequency. So let W is the work required to remove the electron from the metal. So we call this W the work amount of energy required to just emit the electron, means from the conduction band. So if this h nu is greater than W, then electron will eject. So that's how he explained this thing, because it is gonna absorb one photon, and if that energy is greater than W, then electron will eject. So that's how he explained the first observation. Now what is W? Let's see. So W is nothing but minimum energy required to eject the electron from the conduction band, and we measure this W if we see in the band diagram. Then if this is your conduction band, this is your vacuum level, then this energy is called the work function, and this is your Fermi level. So it is measured always from the Fermi level. In the metal this will be like this, in semiconductor this will be from somewhere this here. This is conduction band, this is valence band, so Fermi level somewhere here. So this energy is called the work function. So work function is nothing but amount of energy required to emit the electron. Okay, means just eject, not the kinetic energy. It will just eject the electron from its conduction band to the vacuum level. Okay, so this is called the work function. Now this was the explained observations, means h nu is greater than h nu naught, this is work function. Then electron will eject, and if h nu is less than h nu naught, then electron will not eject. And this is very much or similar with experimental observations. So there can be two cases, when mu is equal to mu naught and when mu is greater than mu naught. So when it is equal to mu naught, then electron will be at surface but not come out. Okay, and when frequency is greater than mu naught, then electron will come out, means it will have some kinetic energy also. Now how we explain the second observation. So it was instantaneous ejection of electron, means if an single electron will absorb the one photon, then it will, if that energy is greater than work function, then it will emit instantaneously. It won't take any time, because this energy will be absorbed instantaneously. So energy will be absorbed instantaneously, that's why it will eject instantaneously. So second observation was also explained. Now third, graphs. So kinetic energy, maximum kinetic energy will be proportional to frequency. So we know this thing. Now what Einstein gave that the remaining energy, means after ejection, the remaining energy will go to the kinetic energy. So this h nu will be equal to h nu naught plus k. Now this k max can be written in the form of A V naught, where V naught is potential. So we can just write this equation in this form, and from here you can see that V naught will be h nu by E minus h nu naught divided by E. So here if you plot the at y-axis V naught and at x-axis frequency, so you will get the slope as h by E, and this y-intercept will be minus h nu naught by E. And this is very much explained, because this is nothing but proportional to kinetic energy. So after a particular frequency, it will have a kinetic energy and it will go in a straight line, means for the mu less than mu naught, it won't have any kinetic energy. Particle means electron won't move, and after a particular frequency it will go to the straight line. So we'll get this curve, and slope will be h by E. From here you can see y equal to mx plus c, where x is frequency, y is V naught, and slope is this h by E, and this is your c, that is y-intercept. So that's how we explained all the things. And h nu is greater than h nu naught. So this is your work function, this is Fermi level, this is vacuum level. Now see, this k max will be independent of the intensity. So how? What is the intensity here in this case? Now intensity is nothing but number of photons falling on the surface per unit area per unit time. So number of photons falling won't change how much frequency it will absorb or how much photon it will absorb, because electron will absorb only single photon of energy h nu. So how much photons are falling, it won't depend on them. So that's why Kmax is independent of intensity. Okay, so it will emit more electrons, but it won't give more energy to the electron. Okay, it will give the same energy whatever we are having, because it is depending on the frequency, not the intensity or the number of photons. So that was the reason that it is not depending on the intensity. Now see, that's all we need to understand about the Einstein interpretation. He explained all the things, but there was one more thing for the NET JRF students, because it can be asked in the interview that if this electron can absorb more than one photon. Okay, so at that time it was not possible. There was only this one photon thing, one photon, one electron. But in the today's era, when we have the strong lasers, or the strong power can be emitted, or the strong intensity, means up to 10 to the 12 watt per centimeter square intensity we can generate. But at that time, or still at this time, the bulbs emit only this amount of energy, approximately 10 to the minus 3 watt. So with this power, it will absorb only one photon. But see, when this intensity is very much increased up to this, then it can absorb more than one photons also. So this was the observation, means this is done practically nowadays. So it is possible. So if this was discovered at that time, then maybe Einstein won't get the Nobel Prize for this equation. He got Nobel Prize for this. So but at that time it was not possible to make a laser of this high power. So that's why nobody was able to verify this thing, that it can absorb more than one photon. So see, we have two energy level, and energy difference is 4 electron volt. And we have frequency only of 2, means we have h nu, total energy of 2 electron volt. Then from this theory, it won't be, means electron volt won't be excited up to this level. But in the today's era, if we use this amount of energy intensity, means there are very large amount of photons are falling on it, then we will see that when electron will be somewhere here with 2 electron volt energy, it will go back, but before going back it will absorb one more photon and it will go up to this side. Okay, so means electron can absorb more than one photon, and it can go to the excited state, or it can be ejected with low frequency also. So this was the observation, and this is called the multi-photon ionization. Okay, so just remember, this thing means not only just 2 photons, it can absorb 30 photons, 40 photons also, depending on the intensity. So, and for the low intensity, this result is very much valid. Just remember this thing. So if somebody asks you in the interview that if electron can absorb more than one photon, then your answer should be yes, but with the condition that intensity should be very large, only then. Otherwise it should absorb only one photon. So try to solve these questions. I will provide you solution in the next lecture. So question is, a 45 kilowatt broadcasting antenna emits radio waves at frequency of 97 megahertz. Then A part is, how many photons are emitted per second? Is the quantum nature of radiation is important in analyzing the radiation emitted by this antenna? If the stopping potential, second question, if the stopping potential of a metal when illuminated with a radiation of lambda is, so lambda is given, is this volt, potential is given, one stopping potential given this. So you need to find the work function of the metal, cutoff wavelength of the metal, maximum energy of the ejected electron, kinetic energy actually. So if frequency is given, third question, 9.5 into 10 to the 14 hertz, incident on metal with work function 2.8 electron volt, and it ejects electron, find stopping potential, cutoff frequency, kinetic energy of the ejected electrons. Next, if frequency is given 7.2 into 10 to the 14 hertz, incident on 4 different metals having work function as 2.14 electron volt, this is for cesium, for aluminum it is 4.08 electron volt, for cobalt it is 3.9 electron volt, and for platinum it is 6.35 electron volt. Then which among these metals will exhibit the photoelectric effect? So which of this metal will eject electrons, photoelectrons, for this particular frequency? For each one of the metals producing photoelectrons, calculate kinetic energy max. So maximum kinetic energy you need to calculate for each one. Now one more question, last question. The intensity reaching the surface of the earth from the sun is about 1.36 kilowatt per meter square. Assuming the sun to be a sphere of radius 6.96 into 10 to the 8 meter that radiate like a black body, estimate the temperature of its surface and lambda of its strongest radiation. Second part, the total power radiated by the sun. So you need to calculate both of these things, temperature and the total power radiated. Earth sun distance is given 1.5 into 10 to the 11 meter. So just try to solve these questions, and I will provide you solution in the next lecture. Okay, then let's end here. Thank you everyone.